Welcome to ENVE 445, Water and Wastewater Treatment Engineering. This is Module 1, Fundamentals of Water and Wastewater and an Overview of Treatment. Overview and Fundamentals, Chemical Reactions and Equilibria. The learning outcomes for this part of the lecture is to understand the fundamentals of chemical reactions and to simplify elementary reactions to form overall reactions. The second outcome is to apply the fundamentals of chemical reactions in mass balance to calculate quantities or concentrations of substances produced or consumed in a reaction. And the third outcome is to apply the fundamentals of chemical equilibrium to calculate the concentrations of different chemical species at a given pH. So just some fundamentals of chemical equations. We have a variety of symbols here that are commonly used in stoichiometry to represent the direction of a reaction or the concentration of chemical constituents or compounds, the phase of a chemical constituent in a reaction, also whether there's a catalyst involved, and if a constituent is volatilized or precipitated out in a reaction. One way to describe a reaction is whether it occurs in series or in parallel. So an example of reactions that occur in series are when you have the conversion of a reactant to a product through a stepwise process. So for example, reactant A forms product B, which then in turn reacts to form product C. A parallel reaction, on the other hand, is when you have the concurrent utilization of a reactant by multiple pathways. And this is when you have a reaction that might have competition with another one. So for example, reactant A is simultaneously converted into two different products, B and C. Elementary reactions refer to individual reaction steps. This is describing what happens at a molecular scale. For example, the decomposition of ozone in distilled water happens through a variety of steps, as you can see here in the 4 elementary reactions shown on the bottom left. An overall reaction, on the other hand, is the simplified version of several elementary reactions that are combined into one overall reaction that just shows what's starting out and what's finishing after the reactions take place. So here on the bottom right, you can see the simplified overall reaction for the decomposition of ozone in distilled water. So let's do this example. Consider the dilution of CO2 in water. Combine the following elementary reactions to determine the overall reaction. So we've got the following elementary reactions of CO2 dissolution into water. And to obtain the overall reaction for this series of reactions, we have to look for things that we can cancel out. So for example, here we've got CO2 gas being converted into CO2 in the aqueous form, and on this next equation we've got CO2 in the aqueous form on the left side, so we can cancel this out. We've got here carbonic acid on the right hand side of this equation, but it's here on the left hand side, so that can get canceled out. Same thing with bicarbonate, and that's just about it. So the overall reaction then would be CO2 in the gas form plus H2O. That's everything on the left-hand side. On the right-hand side of the reaction would be 2 protons plus carbonate. Reaction stoichiometry. Reaction stoichiometry defines the amount of substance that enters and is produced in a reaction. Using stoichiometry and molecular weights, we can predict theoretical masses of a reactant and a product that participates in a reaction. So let's do some examples of manipulating stoichiometry to estimate quantities or rates of constituents in a system. In this example, we want to determine how many kilograms of pure sodium hydroxide are required to neutralize 450 liters of industrial waste that contains an acidity equivalent to 6 milligrams per liter of sulfuric acid. We have here the reaction of sulfuric acid with sodium hydroxide, and we're asked to find how much sodium hydroxide needs to be added to a reactor with a volume of 450 liters if we have 6 milligrams per liter as H2SO4. So first thing we need are the molecular weights of H2SO4 and sodium hydroxide. So for sodium hydroxide, it's 40 grams per mole. For H2SO4, it's about 98. So we'll start with the 6 milligrams per liter of H2SO4. The molecular weight there is 98 grams per mole. So we'll put the 98 on the bottom, and we'll make it milligrams per 1 millimole. Now that we have it in millimoles, we'll use the molar relationship, which is 1 to 2. So this is 1 millimole of H2SO4. And we have a relationship of 1 to 2, like I said. So 2 NaOH, this is moles, to 1 mole of sulfuric acid. Next, we need to convert from moles of NaOH into grams of NaOH, or milligrams. So this is actually millimoles to millimole. And the molecular weight is 40, so we have 40 milligrams NaOH to 1 millimole. All right, lastly, we need to cancel out the liters at the bottom. And so we will multiply this by 450 liters. So that gives us units of milligrams NaOH. And the solution would be 2,205 milligrams NaOH. That would be how much NaOH needs to be added to the reactor in order to neutralize all of the acid. Let's do another example. How much lime is needed to soften a water source with 70 milligrams per liter as calcium, assuming that calcium is present in the form of calcium bicarbonate? And let's also assume that the commercially available lime that we're using is 78% pure on a weight-to-weight basis. For this example, we're trying to determine how much lime is needed to soften water with a given concentration of calcium bicarbonate. So we've got 70 milligrams per liter as calcium, and the molar relationship between quicklime and calcium bicarbonate is 1 to 1. So the first thing we need are the molecular weights of the two compounds of interest. So the molecular weight of CaO is 56 grams per mole. And the molecular weight of calcium bicarbonate is 162 grams per mole. However, we're given the mass as calcium, so the molecular weight of calcium is equal to 40 grams per mole. Therefore, the first step is to convert this mass concentration as calcium into a molar concentration of calcium bicarbonate. To do that, we take 70 milligrams per liter of calcium, multiply that by 1 millimole divided by 40 milligrams calcium. There is 1 mole of calcium in each mole of calcium bicarbonate. So 1 millimole of calcium for every 1 millimole CaHCO3, 2. And then we can multiply that by the molecular weight of calcium bicarbonate. So 1 millimole to 162 milligrams. So we make sure that all the units cancel out, and we're left with milligrams of calcium bicarbonate per liter. And this is equal to 283. Because the molar relationship is 1-to-1 here, we can look at the ratio of molecular weights of calcium bicarbonate and CaO and take this mass, 283 milligrams per liter of calcium bicarbonate, multiplied by 56 grams per mole divided by 162 grams per mole. And that's equal to 98 milligrams per liter of lime. Last step is that we know the purity of our solution is only 78%. So take that 98 divided by 0.78, and that gives us a value of 126 milligrams per liter. Let's do another example. How many milligrams per liter of ferrous iron can be oxidized by 18 milligrams per liter of potassium permanganate? So what concentration of ferrous iron can be oxidized by permanganate if we have 18 milligrams per liter of permanganate? The molecular weight of permanganate is 158 grams per mole. And the molecular weight of ferrous iron is 55.8 grams per mole. All right, so we start with the 18 milligrams per liter. 1 milligram per 100, 1 millimole per 158 milligrams. So 1 millimole goes on the top per 158 milligrams. Now we have millimoles of permanganate. The molar relationship is 1-to-3. So 1 millimole of permanganate per 3 millimoles of ferrous iron. And then 1 millimole of ferrous iron is equivalent to 55.8 milligrams. All of the millimoles cancel out, and we're left with milligrams per liter of ferrous iron. And that's equal to 19 milligrams per liter. One more example. How many kilograms of calcium carbonate will be produced each day if calcium hydroxide is added to a water source containing 50 milligrams per liter of calcium bicarbonate in a system with a flow rate of 1,000 cubic meters per day. And for this example problem, assume that enough calcium hydroxide is provided for the reaction to proceed forward to completion. All right, so in this example, we're trying to figure out how much calcium carbonate is produced in a given reaction. And so here we have the molar relationship between the four chemical compounds involved in the reaction, which is 1 to 1 to 2 to 2. And we are provided with a flow rate, which is 1,000 cubic meters per day. And we're also provided with a concentration of calcium bicarbonate, which is 50 milligrams per liter. And that is as calcium bicarbonate in this example. So I'm going to solve this problem slightly differently from the way I solved the previous stoichiometry problem. So normally I'd written out the entire calculation with a focus on which units were in the top or the bottom and making sure to cancel out all the units. But for this example, I'm going to show you a slightly different way to do the same type of problem. And it's using ratio approach. So first thing we want to do is determine what are the mass ratios of these different compounds. So we know the molar ratio is 1 to 2, but what are the mass ratios? So the molecular weight of calcium bicarbonate is 162 grams per mole. So 1 mole of this has 162 grams. For calcium carbonate, the molecular weight is 100 grams per mole, but if we have 2 moles, it's 2 times 100. In other words, 200 grams. All right, and so we can set up a ratio. We know that 200 grams is produced for every 162 grams consumed. So let's put that on the left side, 200 grams of CaCO3 for every 162 grams of CaHCO3. And we're going to set that equivalent to another ratio, which is what we have in our system. So 50 milligrams per liter, which is the same thing as grams per cubic meter, and multiply that by 1,000 cubic meters per day. So we're multiplying a concentration by a flow rate that gives us a loading. That is 50 kilograms per day. Alright, so that's 50 kilograms per day of calcium bicarbonate. So we're going to put that on the denominator here. 50 kilograms per day of calcium bicarbonate. What we're trying to find is how many kilograms per day of CaCO3 are produced. And notice that the units need to be equal on the right side and they need to be equal on the left side because they both cancel out on both sides of the equation. Therefore, if we solve for x in this equation, we get x is equal to 50 times 200 divided by 162. And that's equal to 61.5. So that's 61.5 kilograms per day of calcium carbonate. Chemical equilibrium. The concept of chemical equilibrium is important in environmental engineering systems, especially for water treatment and wastewater treatment. So let's suppose we have a reaction A plus B being converted to C plus D. The chemical equilibrium constant K is defined as the ratio of products raised to the degree of their molar concentrations in the stoichiometry divided by the product of all of the reactants. And when you see here the reactants and the products in brackets, that's referring to their molar concentrations. So this chemical equilibrium constant is typically dependent on temperature, but in a system that's operating at a constant temperature, it will determine to what degree the reaction will proceed. And just some notation here on the bottom. So if you see that K, for example, is equal to 10 to the negative alpha, then the notation pK is defined as being equal to negative log base 10 of K. In that case, pK is equal to alpha. And this is the same notation used when we talk about pH and the pH scale, for example. The reason why we use this notation is that sometimes these equilibrium constants are numbers that are very low. And so it might be easier to work with them by using the log transformation. Homogeneous chemical equilibria is referring to a situation where all reactants and products are occurring in the same physical state. So an example here would be the conversion of H2CO3 to a proton plus bicarbonate. And another example being the subsequent conversion of bicarbonate into a proton plus carbonate. And for each of these chemical reactions, we have different chemical equilibrium constant. And these constants are for 25 degrees Celsius. So for example, constant number 1, pK is equal to 6.35. For equation number 2, pK is equal to 10.33. Heterogeneous chemical equilibrium refers to a situation where you have substances occurring in two or more physical states. So an example here would be the dissolution of calcium carbonate into calcium ion and carbonate ion. And so calcium carbonate being a substance that is present in the solid form and that dissolves into dissolved ionic species, calcium and carbonate. So here we have, again, the chemical equilibrium equation, and the concentration of solid substances can be treated as a constant, K sub S. Therefore, this equilibrium equation simplifies to K equal to the molar concentration of calcium ion multiplied by the molar concentration of carbonate divided by K sub S. And if we rearrange that and bring K sub S to the left-hand side of the equation, we get this product K times K sub S, which we define as the solubility product constant K sub P. So in this case, we can see that K sub P is equal to 5 times 10 to the negative 9th at 25 degrees Celsius. For heterogeneous chemical equilibria, we define the solution to be unsaturated if the product of the two molar concentrations is less than the solubility product constant K sub Sp. If the molar concentrations are, the product of the molar concentrations is equal to K sub P, we describe that as a situation where the solution is saturated. And the solution is supersaturated if the product of those molar concentrations exceeds K sub Sp. That would be a situation where crystals form until the concentrations are reduced to the point of saturation. So during water treatment processes and wastewater treatment processes, the equilibria of chemical reactions tend to shift to remove undesired substances from solution. So for example, we have precipitation reactions, redox reactions, acid-base reactions, and stripping gas-producing reactions. In precipitation reactions, the formation of insoluble precipitates of undesirable substances is achieved by adding treatment chemicals. Some examples of this include the coagulation in coagulation flocculation processes using alum. So, or another example, using lime to soften water to remove hardness. So for example, we have here quicklime added to a water source that has calcium bicarbonate, and that's used to precipitate out the calcium, in other words, to precipitate out the hardness as calcium carbonate. Redox reactions refer to reactions where there is a change of valence in one of the reacting substances. So an example here being the oxidation of ferrous iron using permanganate to form iron oxides and manganese dioxide. Acid-base reactions are when both an acid and a base are added to the water. They react with each other to neutralize by combining the H plus and the OH ions to form water and also forming a salt solution with the byproducts. So for example, if we have the neutralization of sulfuric acid with caustic soda, that would be an example of an acid-base reaction. Gas-producing reaction is when we have chemical process that involves the formation of a gas product, for example, with an undesirable substance that will escape from the water and into the air. Let's suppose that we have ammonia nitrogen present in the aqueous form at a neutral and low pH, and it's in the gas form at high pH. We can use this chemical process to have a reaction proceed in a direction that involves the majority of aqueous ammonia nitrogen converted to gas ammonia to be stripped out of the water source in order to achieve overall reduction of ammonia, for example. All right, let's do an example problem here. Sodium hypochlorite is produced by adding gas chlorine to caustic soda, producing a disinfectant that's used in water treatment. So this disinfectant, sodium hypochlorite, dissociates to a sodium ion and hypochlorite ion, and the hypochlorite reacts with hydrogen in the water to form hypochlorous acid, HOCl. The ratio, however, of HOCl to OCl is highly dependent on the pH of the solution and the equilibrium of the chemical reaction. This is important to understand from a water treatment perspective because HOCl is a much more effective disinfectant than OCl-. So for this example problem, we want to calculate what is the ratio of HOCl to OCl- for the reaction shown below at pH 6 and at pH 8. And what does that tell you about the efficiency of chlorination at those two different pH levels? This is the reaction of hypochlorous acid dissociating into a proton plus hypochlorite ion. And we have the equilibrium equation here, which has a constant of 10 to the negative 7.5. So under the first scenario, where pH equals 6, we know that the concentration of H plus is equal to 10 to the negative 6th moles per liter. So under that scenario, we know that 10 to the negative 7.5 is equal to 10 to the negative 6 times OCl minus divided by the molar concentration of HOCl. Rearranging this equation to solve for HOCl divided by OCl minus, we get the following. And that's equal to 10 to the negative 6 over 10 to the negative 7.5, which is equivalent to 10 to the 1.5, which equals approximately 32. So at pH 6, there's approximately 32 times more hypochlorous than there is hypochlorite. Now for part B, we want to do that same problem, except looking at a situation where pH is equal to 8. So if pH is 8, then this is equal to 10 to the negative 8th. And our equation becomes 10 to the negative 8th divided by 10 to the negative 7.5, which is equal to 10 to the negative 0.5, which is equivalent to 0.32. So at pH 8, there's less hypochlorous acid than there is hypochlorite ion. And disinfection under that scenario would be less efficient. Overview and fundamentals, reaction kinetics and hydraulics. The learning objectives for this part of the lecture is to apply the fundamentals of stoichiometry and chemical reaction kinetics to calculate the rate of production or the rate of loss for a particular chemical constituent in a reaction. The second objective is to distinguish plug flow from complete mix. We also want to understand how hydraulics affects the apparent kinetics of a reaction in a system. And finally, to size a reactor, assuming plug flow and assuming complete mix, and then consider the differences in the proposed volume required. Chemical reaction kinetics defines the rate of a chemical reaction. So that means the change in concentrations with respect to the change in time. In other words, dC over dt. As a reaction proceeds, the rate of the reaction may change. For example, as the concentrations of reactants decreases, the reaction rate may decrease until the system reaches an equilibrium. Stoichiometry can be used to determine the reaction rates of all products and all reactants if you know or if you measure the rate of change in concentration for any one constituent. So consider the reaction A plus B converted to C plus D. Let's suppose we know the rate of decrease for reactant A. And let's say that rate of decrease is equal to R sub A. If we rearrange the stoichiometry so that we divide everything by the coefficient of reactant A, we get A plus B over A. B is converted to C over A, C plus D over A, D. The relationship between the reaction rates can then be described as follows. The reaction rate for substance A is equal to negative R sub B divided by A. And that's equal to the production of C, the reaction rate of producing substance C, divided by the ratio C over A, etc. Let's do an example problem. Given the following reaction shown below, estimate the loss rates of oxygen and water and the production rates of iron hydroxide and acid if the rate of loss of Fe2 plus is equal to 2 times 10 to the negative 7th moles per liter per minute. Given the reaction shown here above, we're asked to estimate the loss rates of oxygen and the production of iron hydroxide and acid, assuming we know the rate of loss of Fe2 plus. So we have the stoichiometry here. We know the rate of Fe2 plus, so we're going to rearrange this equation dividing everything by 4. Dividing everything by 4. And that's going to give us 1. It's going to give us 1 over 4 for the oxygen, 10 over 4 for the H2O. It's going to give us 1 for FeOH3 and 2 for H plus. Okay, that allows us to write a relationship between the reaction rates of these different compounds. So if we express the reaction rate as the variable R, so R of Fe2 plus is equal to 2 times 10 to the negative 7th moles per liter per minute. But it's actually disappearing from the reaction since the reaction is proceeding from left to right. So we're going to write that as a negative reaction rate. With that said, we can say that this reaction rate for Fe2 plus is equal to the disappearance of oxygen divided by this coefficient here, 1 over 4, which is equal to the disappearance of water divided by 10 over 4. And that's equal to the production of iron hydroxide divided by its coefficient 1, which is equal to the production of H plus divided by its coefficient of 2. Now, since we know the rate of production of iron, we can solve for the rest of rates of production. So let's take the example of oxygen. 2 times 10 to the negative 7th moles per liter per minute is equal to negative RO2 divided by 1 over 4. We solve for RO2 and that gives us a value of 0.5 times 10 to the negative 7th moles per liter per minute. We can use the same approach to solve for the production of ferric hydroxide, R of FeOH3 is equal to, now in this case it's just 1 to 1, but it's negative, so we get 2 times 10 to the negative 7th moles per liter per minute. Reaction order. The reaction rate R is the term used to represent the removal or the formation of a constituent or chemical species. So R is defined as being equal to K times C raised to the n power. R being the reaction rate, typically with units milligrams per liter per day. K in this equation is the reaction coefficient. The units of this is variable and it depends on the type of reaction. And C is the concentration of the reagent, typically in milligrams per liter. N here, the coefficient N is the reaction order. And here it's representing the reaction order, although you should note that in other parts of this course, we might use it to represent the number of data in a sample. The reaction order is typically equal to 0, 1, or 2 in environmental systems. For different values of N, we have these different types of reactions. We call this zero order reaction for N equals 0, first order reaction for N equals 1, second order reaction for N equals 2. And if we look at a plot of the log of the reaction rate with respect to the log of the concentration, we see that the zero order reaction has a flat slope of 0. The one order reaction, the first order reaction, has a slope of 1 to 1, and the second order reaction has a slope of 1 to 2. If the log is applied to both sides of the equation shown in the previous slide, then we get the following reaction, which is how we create this plot shown here on the right. For a zero order reaction, the rate is independent of the concentration of the reagents. The rate of change of the reagent concentrations is constant. So dC over dt is equal to negative K times C raised to the 0 power. In other words, dC over dt is equal to negative k. If we integrate that equation, we get the solution C is equal to C naught minus K times T, where C is the concentration of the constituent being removed, and C naught is the concentration at time t equals 0. K being, again, the reaction coefficient for this particular zero-order reaction. So let's look at two different ways to plot this. If we plot dC over dt with respect to time, we get a flat slope of 0 for a zero-order reaction. If we plot the concentration with respect to time, we get a decreasing trend with a slope equal to negative k, where k is the coefficient. For a first-order reaction, the reaction rate is proportional to the reagent concentration, and the rate of change of the reagent concentration is proportional to the reagent concentration at a given time. So dC over dt is equal to negative k times c raised to the 1. In other words, it's equal to negative kc. If we integrate this equation, we get the solution C equals C naught times E raised to the negative KT. And one thing to note here that the reaction coefficient here has the units 1 over time. Typically, if time is in days, it would be 1 over days, or days to the negative 1. So if we plot dC over dt with respect to time, instead of a flat slope of 0, we get a decreasing slope. If we plot the concentration with respect to time, we get a curve, an exponential curve, where the slope at any given point is equal to negative dC over dt for a first order reaction. So how do we interpret the K value for a first order reaction? Well, if the K values are small, so let's say they're below 0.4 days to the negative 1, as a rule of thumb, we can roughly interpret that K is the fraction of the constituent that decays each day. So for instance, if K is equal to 0.1 days to the negative 1, that's sort of like saying that approximately 10% of the constituent is removed every day. So note that this rule of thumb works only for very small K values. If the K value is larger, then this approximation method will yield larger errors. But as you can see in this example, if our initial concentration is 100 milligrams per liter and the K value is equal to 0.1 days to the negative 1, then what would the concentration be after 1 day? So using this rule of thumb that we talked about in the previous slide, if approximately 10% of that initial concentration is decaying each day, then on the first day, we would have 10 milligrams per liter being removed from this system. So the amount remaining after 1 day would be equal to 100 minus 10 equals 90 milligrams per liter. After 2 days, we would start with the value from day 1, so 90 milligrams per liter. And again, we would lose 10% on day 2, equal to 90 minus 9 is equal to 81 milligrams per liter. On the third day, we'd start with that 81, again, we'd lose 8.1. We would be left with approximately 73 milligrams per liter. So that's one way that you can interpret the K value. In particular, when the K value is quite low. This approximation holds true for the most part. However, note that for this case, in the first order case, the analytical solution is also very simple to calculate. So we don't really need to rely on that approximation. We can calculate it directly. So if we look at the direct calculation, the exact concentration of the constituent after 1 day, 2 days, 3 days, 4 days, we can see that we get slightly different values from the approximate method shown in the previous slide. But after 10 days, you can see here the concentration decreases to 36.8 milligrams per liter. All right, reaction kinetics and temperature. As I mentioned previously, the rate of a chemical reaction increases typically with temperature, um, prov- provided that this increase in temperature doesn't produce some kind of alteration in the catalyst or in the chemical species involved in the reaction. Biochemical reactions also tend to increase with respect to temperature within certain ranges, although there is typically an ideal temperature above which that rate will decrease and eventually will inhibit whatever microbial activity is responsible for the reaction. Usually, K values are reported at a standard temperature of 20 degrees Celsius, which is pretty similar to ambient temperature in some climates. However, we often need to apply kinetics at a different operating temperature, let's say during winter months or in a system that's operating at a higher temperature. So if we plan to use a K value from a textbook or from the literature, it likely has been reported at 20 degrees Celsius or should be reported at a specific temperature. Therefore, we need to modify it based on the liquid temperature of the system that we're designing. If we obtain the K value from experiments that are undertaken at different temperatures, it is important to report or calculate the K coefficient for 20 degrees Celsius along with a constant. That way, we can establish a relationship between the K values at different temperatures that can be used for design purposes. So this equation is called the Van 't Hoff-Arrhenius theory, and it basically shows that there is a relationship between the K values at different temperatures, which is dependent on this dimensionless coefficient shown here as theta. So Kt is equal to K at 20 degrees times theta raised to the T minus 20, where T is the temperature of our system and 20 is the standard temperature where the K value is reported. We can also express this relationship between any two temperatures, T1 and T2. Let's do an example problem. Suppose that we complete experiments of a chemical reaction at two different temperatures, and we obtained estimates of first order coefficients K for each of the two temperatures. Estimate the temperature coefficient theta and use it to predict K at a standard temperature of 20 degrees Celsius. So let's assume that the first temperature was 17 degrees, and for that temperature, we had a K value of 0.1 days to the negative 1. And the second temperature was 24 degrees, and we had a K value of 0.16 days to the negative 1. Another thing we want to note is that residence time in a reactor is not a fixed value, but it's a distribution. So on the one extreme, we might have perfect, completely mixed conditions. But on the other extreme, we might have perfect plug flow conditions. These situations actually never really occur in practice, but they would represent the two extremes of a very mixed system where everything is equal throughout the reactor versus a system that has no mixing and the constituent that moves through the reactor in a plug from the beginning through to the end. In reality, reactors have hydraulics that fall somewhere in between these two extremes. For design purposes, sometimes we might assume complete mix or we might assume plug flow, and that will give us a good enough value in some cases. But in other cases, we might want to perform a tracer test in order to determine the exact degree of mixing and use the data from that tracer test to improve our design. So you can see here in the figure to the right, in a tracer test, we would input a tracer dye into the influent of the reactor, let the dye flow through the reactor as it gets mixed and goes through turbulence and all kinds of different flow conditions within the reactor. And then we would measure the concentration of that tracer as it leaves the reactor. So let's say the step tracer input is started at time t0. And so this would be an example of a tracer study where we start inputting the tracer and we continue to input the tracer at the input location at a constant dose, we would eventually see the tracer concentration at the output start to rise, and eventually it would go up to the level that we are adding at the input. A pulse tracer study is where we're just adding the tracer for a short duration of time, essentially like an instant in time. We're adding a large amount of the tracer, and then we're tracking its concentration at the output. In this type of study, let's say our input was at time t0, we would see a short amount of time before before we were able to detect the tracer at the effluent, and then that concentration at the effluent would increase. It might even spike at a certain point and then would start to come back down. So if we calculate the area under that curve, if this is the concentration of the tracer with respect to time on the x-axis, the area under that curve has a centroid, and that centroid is equal to the mean hydraulic resonance time of the reactor. So that true mean hydraulic resonance time for the reactor is always less than what we call the theoretical resonance time of the reactor, which is calculated as V over Q, the volume divided by the flow rate. So after completing the reading assignment for this unit, here are some questions for discussion in class. The first question: why can't you simply apply reaction rate coefficients determined in a batch reactor experiment to the design of a flow-through reactor? And then the second question being, what are complete mix and plug flow regimes, and are they ever achieved in practice? Some other questions to think about: what would a tracer test result look like for a reactor that followed perfect complete mix conditions? And what would that tracer test result look like for a reactor that followed perfect plug flow conditions? Let's do one more example. Assume that the reaction rate constant for a chemical coagulation reaction was found to follow first order kinetics with a rate coefficient equal to 75 days to the negative 1. Design a flocculation basin for a flow rate of 25,000 cubic meters per day, assuming coagulation to proceed until the reaction is 80% complete. Then compare the requirements, first assuming plug flow, and then assuming complete mix hydraulics. So if the reaction proceeds to 80% completion, we know that only 20% of the reactant will remain at time t. So if C naught represents the concentration of the reactant at time 0, then C naught divided by C sub t is equal to C naught divided by 0.2 times C naught, which can be simplified to 5. So if we remember that the mean theoretical hydraulic retention time is equal to the volume divided by the flow rate, we can rearrange this equation 14.28, which appears in von Sperling et al. 2020, to solve for the volume. So this equation, which appears in that book, is C sub t is equal to C sub 0, or C naught, times e to the negative k t sub h, which is the hydraulic retention time. So rearranging that equation, we move C naught over to the left. We substitute in V over Q for the mean hydraulic retention time. We take the natural log of both sides. Then we rearrange to solve for V. If we plug in the values for the example into that equation now, we get V is equal to 536 cubic meters. So under the complete mix case, the volume required is 536 cubic meters. Now that was the plug flow case. So for the plug flow case, we get that the volume is equal to 536 cubic meters. Now part 2, let's assume now that complete mix hydraulics is true for this reactor. So using the equation that can be found in von Sperling et al. 2020, again, we can rearrange to solve for volume after substituting in for the mean hydraulic resonance time, TH equals volume divided by flow rate. So this equation here is for a complete mix reactor. We have C sub t equal to C naught divided by 1 plus K times T sub H, the hydraulic retention time. So if we take that equation, we substitute V over Q for the mean hydraulic retention time, and then we rearrange the equation to solve for V. We plug in the values then for the flow rate and the K coefficient, and we get a solution for volume of 1,333 cubic meters. So you can see here that the size of the reactor needs to be much larger if the hydraulics follows complete mix condition compared to if we have a plug flow reactor. And this emphasizes and shows the fact that plug flow reactors are more efficient than complete mix reactors. Now, in reality, of course, the hydraulics of a flocculation basin will not follow neither plug flow nor complete mix, but it will probably be a little bit closer to plug flow than it would be to complete mix because they tend to be designed as reactors that are very long and narrow, so kind of getting a little bit closer to the plug flow conditions. Therefore, we know based on our calculations that the required volume has to be somewhere between 536 and 1,333. But if we design a reactor that's more closer to approximating plug flow conditions, we can assume that the volume needed would be a little bit closer to 536 rather than 1,333. So let's suppose we choose a volume of 900 cubic meters. The next step would be to design the reactor by sizing the dimensions, like the depth, finding the length and the width. And we will save that for another time.